All right, so let's continue. Uh, looks at number 4 here. Number 4 is quite interesting also. Means that uh, you have the code here written in behavioral code also, and this is a full code, and you are uh, required to change this coding style from using if else to a case statement, right? So here you can see that the code is using if else statement, and you need to change to if else statement, right? So to do this means that uh, the case statement is also written in behavioral code, yeah, behavioral modeling, and this is if else behavioral modeling as well. So we change to still using behavioral modeling, but uh, uh, we changed from if else to case statement, right? So case statement, just like what I said before, where case statement is actually uh, the uh, the better way of implementing if else statement, right? So in this case, what we want to change is actually what inside this always block, because the declaration part should remain the same, right? So here I will not write the declaration part. I just focus on the always block. Yeah. So at the always block, we can all right write the code like this. Still the same. Always a or en. You can have begin. No need to have begin, because when you want to code in always block, so sorry, in case using case statement, maybe the best way is to have the to understand the behavior of the code of the circuit that we want to create first. So before we start, maybe we need to have the Boolean equation, not the Boolean equation, sorry, the truth table. So let's have a truth table for this. The input, how many input that we need to have? We have a 2 bit, yeah, so it's a 2 bit and en 1 bit 3, correct? So we will have we can start with en, and we can have a1 and a0, and we can have the 0 0 0 0 0 1 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, right? So in A can have can be something like this, right? And what about the output? So we have Z0, Z1, Z2, Z3. So yeah, straightforward. So we can have Z0, Z1, Z1, Z2, Z3. Okay. If A equal to 0, Z0 equal to 1. Uh, if En, we have many if here. If En means that if En equal to 1, so this part, it will be this part only. All right, this part only when En equal to 1, yeah, not when En equal to 0. So we look at this part. If En equal to 1 and if A equal to 0, Z0 equal to 1. So what we can do is this. This is A, oops. This is when A equal to 0, right? So we will have Z0 equal to 1. The other Z should be equal to 0. Yeah, because only Z0 equal to 1. Else, if A equal to 1, means that if A equal to 1, must be this part. Must be this part. So we have Z1 equal to 1. And the others should be 0. And if A equal to 2, means that this one. So we will have Z2 equal to 1. Others 0. And if A equal to, or else, yeah, Z equal to, means that if A equal to 3 in this case, because we have A 0 0 0 1 1 0 and 1 1. So the last one should be this. It looks like a decoder here, right? And if En, right, else Z equal to, yeah, else Z equal to 0, means that if En equal to 0, Z0 equal to 0, Z1 equal to 0, Z2 equal to 0, Z3 equal to 0. Means that if En equal to 0, means that this part. If En equal to 0, all are 0. And this is exactly a decoder, right? A decoder. Now, how to write the code for this using case statement? This is easy. In your notes here, this is how, and also in your assignment, right? So this is 2 to 4 decoder, yeah, with enable input. So if I write the code in for the always block only, you can write this way. en or a. So I can have case. I can combine the signal where I can use concatenation syntax like this, en a, right, to combine en and a. And if we have en equal to 0, or I can write in decimal, just put 0, right, to represent this. Or you can write, yeah, because Verilog is quite flexible, you can write number in decimal, or you can write number in hexadecimal, or you can write in binary. So if you want to write in binary, it can be like this: 3 b 0 0 0, right? But I want to write this fast. I don't want to write in binary. I just write 0. So I can have begin, because we have 4z there, z0. So I can have z0 equal to 0, z1 equal to 0. Yeah, this is waste of time, because this one we all are 0, right? We can use default. So we can have start with this one. So we can have 4. So if a equal to 4, 4 or 1 0 0, yeah. So I can say that z0 equal to 1, done. And if 5, z1 equal to 1. If 6, z2 equal to 1. If 7, z3 equal to 1. And the last one is default. And because we have many z, so you need to have begin, z1 equal to 0, z2 equal to 0, z3 equal to 0. I forgot z0, so I can write here z0 equal to 0, same thing. And you need to have n case here at the end, right? So this case is starting here and end here. And because you have many z here, so you need to have begin and end for this default alone. And if you want to write like this, actually you need to have or initialize the value of z to be 0 first. So what we need to do is actually okay, before the case statement, so we need to have z0 equal to 0, z1 equal to 0, z2 equal to 0, and z3 equal to 0. And of course, if you have this, yeah, means that you have two statements already. This statement, many statements, 1, 2, 3, 4, and this case statement. So you have 5 statements. So you need to have begin and here, right? So that is how we change these two case statements. And there are many ways actually. You can use this style of coding. Also the same, but here cannot, yeah, because you have if else. We don't want if else. We don't want to use case statement. So this, yeah. this is the case. All right, so that will be the answer for number 4. And you can check in quarters, right, to see the answer. Okay, any question for number 4? Number 5 and number 6, this one is actually the advanced coding style. I haven't teach you in the class, but and it is not officially teach in the class, yeah, but you can study this by running this code in quarters to see what is the output. This one is okay. This one is for loop, right? And in this test, this is not asking up to this level yet, but in the final exam, yes, right? So for the test, number 1 to 4 is sufficient for your test. It's okay for your test, right? Okay, any other question before we go to the next? I have more question actually to discuss.
For test, they will ask like this question or more complicated.
Yeah, just like this. Just like this. But again, it's not 100% like this one. Maybe just like this. For example, want you to derive the 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 circuit. Yeah, this one asks you to derive the Boolean equation, right? Maybe in the test, I ask you to derive the uh, the logic circuit, right? So you need to draw the logic circuit. But of course, in order to draw the logic circuit, you need to have the Boolean equation, yeah, something like that. But the level of difficulty is like this. All right. So let's look at the previous test question to see how uh, the test is. And the question I think I have shared with you in Telegram already, right? Yeah, it is in the Telegram. So this is the previous semester, yeah, semester 2, the test, 1 hour. And for this, you have four questions to be answered in 1 hour. So let's look at the first question. And okay, so Suresh, this is easy or difficult for you? Q1. Is it easy? Too easy or difficult or too difficult? 3 level of difficulty. Huh?
Half, half, half,
Half,
half
half,
lah.
half,
Medium, medium.
half, half.
Half
So
easy, half difficult.
half easy. Yeah. Don't make conclusion yet. Read the question first. Okay, figure Q1 uh, shows the lookup table that is used to implement a logic in an FPGA. If the LUT cell is programmed with the logic as shown in the figure, determine the logic equation that it is implemented. So to answer this, we need to go back to chapter 1, right? Where the answer, not the answer, the concept is given here, right? So actually the function here, the output f here will depend on what you have in the cell here. So for example, if you want to implement an what is this? This is XNO, right? So if you want to implement XNO, what you need to do is you put uh, the value, the output for XNO gate for two input here. This is two input gate, right? We have X1, X2, one output. So this will give you XNO. XNO. So the XNO is this, the equation is this. And now back to our question. So you have this in the cell, yeah, 0, 1, 1, 0. So what is the the gate here? Yeah, what is the gate here? Is it an AND gate, an OR gate, or what else? Okay, so still difficult. So you have A, B. Come on, tomorrow is your test.
XOR gate.
Yeah, 0, 1, 1, 0. But if you still don't know what is this, now you can actually give the Boolean equation already, right? Determine the logic equation. The logic equation is Boolean equation, right? So here you see, so this should be f equal to a bar, b, or a, b bar, right? So this is the answer. Is that difficult? I don't think so. This is the
No.
uh, so this is the easiest one. Actually, free marks, 5 mark is free for you to collect. But yeah, you need to understand how this works, right? So if you read the notes, then should be no problem for you. Or if you understand what is here. Okay. Now looks at the uh, question number what? Number two. Number two, in a digital hardware or system or circuit, anything, negative number are represented in two's complement format. With suitable example, discuss the reason why two's complement representation is used instead of other formats. This one you need to go to chapter 3, right? Go to sign number here, sign number representation. So the question asks you, or what the question one is that uh, if you are or why the two's complement representation is used in digital hardware. Means that in computer, in everything that we have today, the microprocessor and in digital system use two's complement to represent a negative number. That is the question, right? So to answer this, you need to understand this, why we use or why we have the two's complement representation, why we have the sign and magnitude representation, right? So how many kind of representation that we have? We have three kind of representation to represent most the negative number, right? So this is because in hardware, when we want to perform subtract, all right, or any calculation uh, that using or that uh, involve negative number, right? So for example, if you want to implement, yeah, you can use this as an example as well, right? For example, if you want to implement 5 minus 2 in hardware, what what to do? Okay, so remember in hardware, designing a subtractor, this is subtract, right? Sub. So designing negative, not negative, subtractor is not that easy. Okay, so what we have is we have an adder. Remember, we learned adder, right? We have an adder. So what we can do is we use adder and add to the negative number, negative 2, such that we get number 3 in the end. Okay, but the problem now is how to represent a negative number in digital system. In decimal, we human, we use decimal, right? So negative is easy. We use sign, minus sign to represent negative 2, minus 3 to represent negative 3. But in digital system, because digital system we use binary 0, 1, 0, 1, remember? So how to represent negative number? How to tell the hardware, how to tell the computer that this is negative, right? Can you write this negative? No, because how to implement minus in hardware? Okay, we can implement 0, implement 1, remember, using transistor, using switch, all right, but minus, how to do? Okay, so this is we need to thanks to the people, to the one who give the idea, yeah, who invented this idea. So we use this uh, digit, yeah, logic also to represent minus, all right, where 0, yeah, if we have 4 bit like this, the MSB is called a sign bit, where 0 represent a positive number and negative represent 1 represent negative number. Okay, so there will be 3 type of negative number representation in hardware, in binary. The first one is called sign and magnitude. All right, so everything is here in the notes. All right, the first one is sign and magnitude. And whether we can use it or not, we need to look at this. So how to use sign and magnitude? So for example, if we want to represent minus 2 in in the, in binary, so of course the sign is 1 to tell the hardware that this is negative, and the magnitude and the remaining bit is the magnitude of the number. So in this case, for example, if our system is 4 bit, yeah, small system, 4 bit, so the remaining 3 bit, 1, 2, 3, 3 bit will represent the magnitude. So number 2 is, yes, 0, 1, 0 is 2 in binary. So this is minus 2 in binary system, right? Represented in sign and magnitude representation, we call it. Now, how to do this in hardware? So what we do is we have number 5, 4-bit in hardware, and remember we need to use adder, so add plus. Yeah, we want to do this. 5 plus negative 2. So this is number 5. Negative 2 is this in sign and magnitude representation, 1010, which is minus 2, and try to add using adder. This is hardware. Yeah, the adder circuit. So we add. What we have is 1 1 1 1. And look at the result here. Yes, this is negative, where we should have plus 3. This is wrong already. And also the magnitude is also wrong. We have plus 7 instead of, no, minus 7 instead of plus 3, which is wrong. And when you change to other number as well, or for example, you want to have minus 3 or minus anything that that we have, yeah, and you will have, or you will get wrong result always. This implies that sign and magnitude is actually no use. Sign and magnitude representation is no use in hardware. We cannot use this. Definitely cannot. Now we have another representation. We call it first complement, right? So how we do first complement? So again, minus 2 is represented in the first complement representation, where we have number 2, 4-bit. We just complement it. We have 1101. So this is called first complement, right? And let's look at this. We have 1101 to represent minus 2, and we add. Now let's add. So we have 1 plus 1, we have 0. We have carry 1. We have 1 here, right? 1 plus 1, we have 0. We have 1. 1 plus 1, we have 1 0, right? And look at the sign. Yeah, 4-bit. Yeah, this is not the sign. The sign is here, positive, which is good. Look at this. This is 2, number 2. Is it correct? No, not correct yet. But if you add 1 to the result, you will have 1 1 0 0, right? Where this is 3, and this is correct. And if you change to add a number, you will need to always, yeah, for example, in this case, when you look at the note, yeah, everything is here. For example, you want to do this, plus 5, minus 5 minus 2, you need to add 1 to get the correct result, and so on and so forth, right? When you change the value, you need to, yes, sometimes you need to add, but sometimes you need to, no need to add, right? But this implies that you need to add here and add here, means that you need 2 adders at one time. And also this implies that first complement actually can be used in hardware to do this, to do 5 plus minus 2, or minus what, 5 minus 2 minus 3, or whatever, right? Can be used first complement. But the modern computer that we have today not using first complement to represent negative number. This is used to complement. This is because that, for example, again, we want to do this 5 minus 2. Okay, so number 5 still 0 1 0 1 in binary. This is 5 Minus 2 in 2's complement is this 2. We complement, we have 1, 1, 0, 1. You plus 1, you need to plus 1 to get second complement, right? You have this. So this is minus 2 in second complement. So you use plus because this is adder. 1, 1, 1, 0. And try to add this 1. Here you have 0 plus 1, you have 1. 1 plus 1, you have 0, 1. 1 plus 1, you have 0, 1. And this is bit number 5 already. You can ignore. And look at the result here. 0, 0, 1, 1. And this is minus 2, of course. The result is positive 3. And this is correct. And if you look at other example here, you will always get the correct answer for 2's complement subtraction, right? Without required to add again to the answer here, just like in the first complement addition, right? Second complement addition is this. And this is why we use second complement in the hardware, in the computer hardware. So again, to answer this, it looks too long, right? But this is just my explanation, right? But if you understand this, you give the example, for example, the same 5 minus 2 and explain the things to answer this, then should be no problem for you, right? And this is 10 marks, right? But of course, you need to understand why we use to complement in the digital hardware. And actually, the answer is here. Read here. Read what you have here. Okay. Any question?
No, doctor.
Okay. Right. So now go to the next one. This one, is it difficult? Q3? Suresh? Oh, I always ask Suresh. Suresh, yeah. And T. What about others? Is it difficult? Number 3? Looks like difficult, right? Because the question is quite long.
Depends on the mark, doctor.
Depend on the mark.
More
No,
mark,
not really.
more.
No, 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 no. Not that way. More marks means that you need to do more. All right, means that the step, there are many steps to do, but not necessarily this is difficult, right? So let's look at Q3. Suppose that you are an RTL design engineer. Uh, RTL design engineer is the engineer that write a Verilog code to design a digital system. That is called RTL design engineer, right? So if you're interested to work in digital design field, so the post is RTL design engineer. Okay. In a leading electronic design company, your design team need to design a system based on the functional block diagram below here, where module M0 and M1 are the IP core that are required to be used in the design. Means that M0 and M1 here is the design that your company here buy from outside, the third party one, or other circuit. Yeah, in other words, is other circuit that you need to use in your design, right? Or a sub circuit, a sub module. And this one, of course, you need to design. the multiplexer here and the combination, the logic gate here, right? Fraction of the Verilog code for the for module M0 and M1 are given in listing Q3. So you can see in listing Q3, yeah, we have the M0 and M1. So all the information is here. Should be no problem now. We have the description of M0 and M1. And M0 and M1, the body, the content we don't know, but this is not a problem because we only want to use, yeah, the M0 and M1 in our design. So we don't need to know what is inside, all right? What we want to know is how we connect this to this. That's it, okay? So we have M0 and M1, so it should be no problem here. Redraw the FBD and label all the signals and write the Verilog program for the FBD. That is why we have 18 marks, because you need to write a Verilog code. Redraw the FBD. So in online tests like this, so to redraw, actually no need to redraw. You can actually capture this and paste on your answer, right? So here, for example, if we want to label this, so we need to look at the yeah, M0, M1. So we have M0, we have this. This is the port that is available. So we have A, what is that? ABX, ABX. M1, we have C, D, and Y. We have C, D, Y, N. So you can have this is N, this is Y, also no problem, yeah, because this is not described here, which one is N and which one is Y. So in this case, because this is X, so this is N, Y, and N, right? And that's it for the M1 and M0. Now we want to write the code for this. Yeah, so we need to have the name, port name. So you can have any port name that you want, right? So for example, you want to use A, B, C, D here. So it should be no problem. But A, what is A? Here A, B. So A and B here should be 2-bit. Yeah, remember, 2-bit. And let's say, for example, this is S. All right. And the output here is maybe we have I or any name that you want, right? So because the question want you to label everything that you have, you just label it. Maybe this is M, this is I, what else? This is N already. Maybe this is J, this is K, this is F, right? Just label it on the signal that we have, right? This you can use X, this you can use Y, because this label will be used in order to write the Verilog code, yeah, to answer this. So again, the question is designed such that it is like it is an open-ended question. It's an open book question, right? So you can see that this one you have an option whether you want to use I, J, K, M, N, or whatever name that you want to use. Yeah. So it is easy for me to know whether you get the answer from your friend or not, or you discuss this or not. All right. So whenever the answer is the same, which should be the same because it can be any name. All right. So if the answer is the same, means that you are cheating, right? So please avoid that, because the question, this is open book, open online test. You can access to internet, you can communicate with your friend, right? And you can have your friend answer. You can send the answer to your friend, right? But it is designed such that I can detect whether you get the answer from other or not, right? So this can be any name, right? And of course, the Verilog code also, right, can be any code, right? This is unique. Yeah, your code should not be the same as your friend, right? Okay, so we have the label already. So can you write the code for this? Suresh, can you write the code for this?
Maybe can.
All right. If you cannot write the code for this yet, means that you're not ready for the test tomorrow. Make sure that you can write the code for this. Okay, let's look at this. Yeah, how to write the code for this. Okay, let's use this. Okay, let's see whether this is difficult or not to write the Verilog code actually. Okay, what you need to do is actually to practice. So first thing first is you need to have your module name, right? For example, we name it as Q. This is question number what? Number 3, Q3. And we just need to list all the port that we have here, right? And remember, your code must be based on your circuit. So you have what? You have A, B, C, D. So list it: A, B, C, D. What else? You have S. S. You have M. You have, yeah, F. So the others is the internal wire. N is internal wire. Y, X internal. I, J, K, all are internal wire, right? So here you can have the input. So specify what is the input. So here you have 1-bit input and also 2-bit input. So A and B is 2-bit, right? So can need to be written like this. And we have 1-bit input. S is 1-bit. M is 1-bit. S and M is 1-bit, right? And we also have all the wire here. So we can have wire. X, we need to know what size of X. So what is the size of X? Is depend on this. X is 1-bit. All right. N and Y is also 1-bit. So should be no problem here. So in this case, X is 1-bit. So we have X. We have N and Y is 1-bit. Okay. What about J and K? J and K is also all are 1 bit, right? So it's depend on how you want to describe this part, yeah? Whether you want to have or not. So for example, if we want to use structural modeling, so we can have I, J, K, right? And we have output F 1 bit. So that's it. Now we want to describe this part, do the connection for this part. So we need to call this M0, M1. So first M0, and of course we need to name it, yeah, in Verilog. So let's name this as C0, this one as C1, right? So this is C0, and do the connection now. So how the connection? So you can use the port name connection where you need to have dot A connect to A like this, or you can have the position connection. A here is connected to A here, so just write A, and this B connected to B, and the last one must be X. X here is connected to this X, so must be X. And you have M1, and this is C1 in our case. And the connection is need to look at this, the position here, C, D, and Y. So we need to follow that, C, D, and Y. So C here is connected to C, D, N is connected to N, Y. Right? Done. We have this already. Now we want to describe these marks. So to describe this mark, there are many ways. You can use data flow modeling, you can use behavioral modeling, you can use structural modeling, right? So I think the best way is to use data flow modeling. Assign I, the output here, equal to I here, equal to, use this. So this will give you this multiplexer, yeah? How to do this? You need to go to chapter 2, right? Or if you don't know how to use this, you can use behavioral modeling, where you can have always block. The sensitivity list X, Y, S, X or Y or S. So if S equal to 1, I should be equal to X, else I equal to Y. So this is the thing. But again, if you use always block, I is now not a wire, but this is a array. So this is not correct. So you need to have this. Right? Remember, if I here is now array, because you assign X to I inside the always block. Right? Now you get the multiplexer. And last one, you can describe this one. So you can describe using data flow modeling or structural modeling. So let's use structural modeling because we have all the signal name here. All right. So we can start with this gate. So you can have N, I, J, the output, I M, the input, right? And this one is an AND gate also, N, K, N, and M. And the last one you have OR gate, and the output is F, J, and K. Done. And module. All right, because done already. So we have all this part, this is this one, and this is this too, right? And here you can describe using data flow modeling as well, where you can have something like this. F assign F equal to, here, F is actually I and M, I and M, or N and M. So you get F also. But now you not require this J and K, so you can remove J and K in this case if you use data flow modeling. So it depends on how you want to code this thing, right? And again, you need to practice in order to know how to do this, all right? And the example is a lot in the notes, right? And again, this is why I asked you to do the assignment and also any practice, yeah, in order to gain or get the skill to do this, right? So let's see tomorrow whether you are ready or not. Yeah, you have almost 24, more than 24 hours, one day, right, to get it done. All right. Any question for this one?
Doctor,
Yep.
if we refer to the knot, is considered cheating.
No.
Refer to the knot example.
No. No.
Exactly like the code like
Yeah. No. Yep. Because the question is not exactly will not exactly the same as the not. Mm. And I think the last one is easy. Uh, where you need to derive the logic circuit from this, and this is if you look at this is just a decoder. Yeah, just a decoder. And you need to derive the logic circuit, and not the Boolean equation. And of course you need to derive the Boolean equation first in order to derive the logic circuit, right? So this is a 3 to 8 decoder.
So, doctor, for this question,
Yeah.
for this question, sorry,
Yeah.
we need to do the truth table first, then only we do the logic circuit.
Yeah. 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 Right. This is actually similar to the tutorial question, similar to this one, right? This is, yeah, similar to this one, except that the value is just different. Oh, this is not 3 to 8 decoder. This is not a decoder. This is easier than that. Yeah? Easier than that. This is very easy. Yeah, get the truth table and you get the answer. Try to do this. All right. If you have question, then you can ask me through Telegram. This is more easier than this one. Right? This is 3 to 8 decoder, a bigger circuit.
So, doctor, the question 4 is need us to write the Boolean equation.
Yeah. You need to have your Boolean equation
Oh,
and draw the circuit. Yeah, the logic circuit. Mm. It is easy actually, very easy. Okay, so this is test question for the previous semester, and this semester for tomorrow you have only 2 questions actually.
equation for 1 hour.
Yeah, 2 questions for 1 hour. And the level of difficulty is like this. Yeah, not means that 2 question less than this, and your question is difficult than this one. No. All right, the level of difficulty is still the same, but the uh, the number of question is reduced. So actually, you are a lot more easier than this. Right? Actually, this one is not that difficult because if you look at Q4, yeah, you can answer this in not more than 10 minutes. Q1 is very simple also. Yeah, not more than 5 minutes should be done. Okay, so any other question? I have also maybe if you want to see the this is another. This is semester 1 test. The previous semester, this is 1.5 hours. Here you have part A, part B. You have part A objective question, and part B you have subjective question like this. But you have 1.5 hours. This one is if you want to you want this question, I will share in Telegram also. Yeah. Okay. So any question? We are 4:40 now. So if no other question, yeah. So okay. So if there is no other question, we will end the session. So again, my advice is that you have 1 hour, and please read the question carefully, and If you have any questions, you can ask through Telegram, right? Um, what you need to do is you need to practice, and you need to have fundamental knowledge in digital electronic. Yeah, for example, derived Boolean equation, derived circuit. That one is the basic that you need to have. Uh, and how to write the code. For example, if you have the circuit like this, right? This is similar to the previous test that we have discussed. Yeah, but the circuit structure is different. So you might get the idea already how the question should looks like. Yeah, if you need to write the Verilog code for the circuit, so the circuit must have something like this. Yeah, where you have the module, you have the mark, you have the combinational circuit or whatever, right? So how to write the code for the circuit that looks like this. So this is actually a combinational circuit, and this is for uh, chapter 3, right, that we have. This is subtractor. Yeah, you learn in combinational circuit chapter 3 as well, right? This is also the same. So you should be able to write the circuit if you are uh, given the you should be able to write the code if you are given the circuit or block diagram. You should be able to convert from the code to block diagram as well, or from the code to the circuit. Okay, so tomorrow we'll be at 8:30. All right, 8:15 you should be able to download the test question. 8:15, yeah, you should be able to download the test question already. And 8 8:25, yeah, 5 minutes before the test, I will give you the password. Yeah, because the test question got password, right? So you download, make sure that you download the question first, and yeah, you can open the question 5 minutes before you can start, so you can read everything 5 minutes, and make sure that you answer in one hour, and I will give you extra 5 minutes to upload your answer. All right, so please don't upload after or 1 minute before the time in order to close, yeah, to close the link, because I will set the link such that it will disappear after 9:35. All right, so make sure that you answer 1 hour and convert to PDF and upload before 9:35. Okay, so if no question, so we will end here today. And good luck. Do you have any test today?
Yes, today.
Oh, what test?
ECAT doctor. ECAT doctor.
ECAT. What is ECAT?
Electronic communication.
Electronic circuit analysis
Electronic
design.
circuit analysis
Oh,
design.
electronic circuit analysis. You call it ECAD. Huh, okay. Um, yeah, that will be analog part, right? Okay, good luck for your test tonight and also tomorrow.
Thank you, doctor.
Okay, welcome. See you tomorrow.
Thank you, doctor. Thank you, doctor.
Welcome.
Thank you, Doctor. Thank you, Doctor. Thank you, Doctor. Thank you, Doctor.
Oh,
Doctor.
yeah. Check. Oh, you are here also.
Yeah.
You are
I
everywhere. Okay.
have a question for the just now the tutorial question 4.
Oh, question 4. Tutorial question 4. Yeah.
Let me can I share my screen?
Yeah, sure. Okay, I stop presenting first.
I need to re-enter again.
Oh, yeah. Okay.
Share my screen.
Uh, I'm not recording the class today, Zarim.
Can Doctor see my screen?
Yeah.
Is this correct? Just now I got all your
Ah,
solution
I see.
question 4. It's a bit
No.
let me readjust the screen.
Okay. Uh, where's your screen?
Let me reshare again.
Okay.
You,
Yeah.
so this is my solution for question 4.
Uh-huh.
Is this correct? I mean,
Uh, Not all correct. I mean, Z here, because you declared Z as single individual signal, Z0, Z1, Z2, Z3, and in your case statement, you cannot use Z 4-bit like that.
so I will need to remove the,
If you want to use this way, you need to declare Z as a vector.
okay,
Mm.
vector means,
4-bit. So just in your module name there, you have only one Z.
oh,
Mm. Okay. And the output there, you need to declare Z as a 4-bit signal, 4-bit vector. Yeah. 0 to 3 or 3 to 0, doesn't matter. Okay. Then you can use that. And in the case statement, why you have Z1 there?
okay,
And should be EN first, not A first. Because if you have A first, uh, if you have A first, so the first two bit is A, not EN.
oh, okay,
Uh, right?
And this one is this correct? Can I use this?
Yeah, that one is correct. And then again, the arrangement, because because the arrangement is Z0 if 100, right? En equal to 1, A equal to 0, 0. So Z0 will be equal to 1, right?
Z0 equals to 1.
Is it
Which one
correct?
you're referring?
No. If you look at this,
This
at
one.
the, yeah, at the question if asked one, if, yeah, if A equal to 0, means that 0, 0. So Z0 should be equal to 1, right? So if you arrange like that, so your vector must start with 0, not 3. 0 to 3. You get
That
what I
means,
mean?
sorry,
No, the Z, the
is
right,
that,
the output declaration there,
or this one?
must be 0 to 3.
0 to 3.
Yeah, uh,
Because of,
yeah, because look at the Z that you have in the case statement.
oh, yeah,
So
okay.
the first bit will be Z0.
Mm.
After B will be Z0.
Oh,
If you have 3 to 0, so the first bit, Z in the first one here must be
there
0
must
0
be,
0 0 0 0 1.
oh, okay, that means the
Looks at the
position has to be,
position, yes,
oh, okay,
and this one
then,
is okay.
okay. So
Mm.
this one usually how many marks? 12 marks.
How many marks? uh, Normally depend on the difficulty level. This is the difficulty level is, I can see that this is just not too difficult and not too easy, right? So normally the marks will be given as, if the module name is actually the port list is free mark, normally 1 mark. Hmm. The if the declaration correct for input, yeah, so depend on uh, the input correct, yeah, both A and En correct, you will have 1 mark. The output 1 mark, and the rack declaration also 1 mark, uh, right?
Roughly like 10 marks.
Yeah, roughly like 10 marks. And also it must be correct as well, because the case statement, for example, right? Uh,
Mm.
how you arrange En and A, if wrong, you will not get a mark. Just now you
Oh,
have AEN, right? So means that everything is wrong already. So you will lost the marks there. So make
okay,
sure that
okay.
uh,
Thanks,
be,
doctor.
yeah,
Now I understand.
because if you have the different
Mm.
arrangement, yeah, it will produce the different result already, different circuit, different result. Mm. But if you have the structure like this,
Mm.
for example, you understand that this is a decoder, right? So
Mm.
so I know that you understand this is the decoder, so you have at least half of the mark already. Although the
Oh,
description is wrong, right? More than
okay,
half lah, more
doctor.
than half. Mm. Uh,
I try to prepare much more better for tomorrow.
yeah. Okay. Good luck.
Thanks, doctor.
Yeah. So it's actually
Mm.
the way to learn this course is uh,
Mm.
you need to, yeah, you need to write the code like this, and to get the skill, right? To know,
Mm.
for example, to know just like just now the arrangement, how to declare that, whether 0 to 3 or 3 to 0, right? The vector. So
Mm.
what you need to do is you need to run in quarters and see the result. Then you will start to learn from that.
Okay.
Uh, so
Using same way like the assignment, right?
yes, yes, yes. You do a lot of practice. Use the software, yeah, because you have the software already, and you can run. But actually, it is fun. You can mix, have a different configuration and see the result, and you can start to figure out that, oh, this is not that difficult. Yeah.
Mm. Yeah. Actually, I feel like there's a pattern in it. So when we master that pattern, right, then I think most probably the code shouldn't be a problem.
Yeah, yeah, that's it. That's it.
Okay, I
Uh,
try and see how for tomorrow.
and more interesting later on when we learn chapter 4, chapter or more advanced chapter, we can see that designing a custom digital circuit is very very fun, very interesting, where we can design up to a processor level.
Hmm.
Mm.
Okay, okay. Sounds interesting.
Yeah.
Okay. Thanks, doctor.
Okay. Welcome.
Okay, bye.
Bye. Helmi.